Hello everyone, welcome back to the series of videos on operating systems. So this is part 17 and in this video we'll be talking about the differences between stack and heap section. So here are some of the things which we'll be looking at. So we'll see what is the difference between stack and heap. We'll also try to look at the various advantages and disadvantages which are provided by stack, also which are provided by heap, and then we'll also see we'll also look at the reason for the opposite growth direction of stack and heap. So as we have discussed in the previous video, this is how the process structure looks like in the main memory. So this is the address space. This is the address, zero and max address of a process, and these are the process. These are the various components in the process structure. So we have the text section, which holds the code, and then we have the data section, which has the various global variables, and then we have these two, stack section and heap section. So stack section, it stores the various local variables, the function parameters, and the return addresses. So all those kind of stuff are stored in stack. And then we have heap. So heap memory will store this is the memory which gets allocated dynamically. And there is an interesting part where which talks about the direction of growth. So from this diagram, it is clear that heap is growing in upward direction and stack is growing in downward direction. So the reason for the growth of direction we'll look at in the future slides, or in the coming slides we'll see what is the reason for this growth in opposite direction. So we'll just talk about stack first. So stack, this is like a memory region which is used for storing temporary variables. For example, it could be local variables, it could be function parameters. So for example, if we consider this code here, so this code is just text. So this would be stored in the text section of the process. And assuming we call this function by passing parameters 4 and 5, then these parameters will be stored in stack, and the return value, that is 4 plus 5 9, so that will also again be stored in stack only. So here this is stored in text section and the parameters will be stored in stack. So just for an example, I've put up this small snippet of code. So when we talk about stack, stack is last in first out kind of a data structure. So assuming this is the stack, so whatever item comes first will be the one which is going out of stack last. Or in other words, it is whatever comes last will be the first to go out. So last in first out kind of data structure. And we make use of stack only when we know what is the size of the or so this stack will be usually used for static memory allocation. So by static memory allocation, what I mean is, so we should know before compile time how much data we need to allocate. So for example, if you want to create a stack of say five integers, so this five number of five integers, so this number should be known before compile time. Only then we'll be able to use stack. uh, if at all there is a requirement where we need more than five integers, then in that case it would lead to the stack overflow error or issue. So where we have a stack of only five integers, but if we try to add one more integer, then it causes this overflow issue, which is popularly known as stack overflow. And stack, it grows in the opposite direction as heap. So as we've seen here, it is growing downwards and heap is growing upwards. But this downward growth and upward growth, this is coming from historic reasons. So it is not necessary that stack should always grow downwards and heap should always grow upwards. It can also be the other way around, where we can have a stack which is growing upwards and heap which is growing downwards. But in early design structures, we had stack growing downwards and heap growing upwards. So that same convention is currently also being used, where we have this downward growing stack and upward growing heap. But there are many architectures where we have the other way around also. So it's not necessary that stack should always grow downwards and heap should always grow upwards. And also, when we talk about thread, each thread will have its own stack. So we'll deal with threads in the coming videos. So for now, we'll just see that we just have to like know that every thread has its own stack memory. I mean stack memory section. And so whenever we have the data in stack, as soon as like whatever function we have here, as soon as this program like comes out of scope of this function, whatever data we had in the stack gets automatically deleted. So as soon as we like return from this function, whatever data was there in the stack will be deleted automatically. So we don't have to explicitly delete the contents in the stack. So assuming we like push 4 here and we like push 5 also, then we add both and like push 9. And as soon as we like return from this function, the contents 4, 5 and 9 which are there in stack are like automatically deleted. So we don't have to go and like delete. So it gets deleted automatically. Also, the stack size is fixed. That's the reason why we like say that stack is used only for static memory allocation. So before compile time only, we'll have to like decide what amount of stack we need. So that stack size is always fixed. And once we like cross that stack limit, it'll like lead to the stack overflow issue. And when we compare it with heaps, stacks are like always faster because memory allocation is like way simpler because deletion is like happening automatically. It's as simple as just moving that stack pointer. So when we talk about heap is that memory which gets allocated dynamically. So you make use of these malloc, like free malloc or new, for example. All those kind of functions are needed in order to like create dynamic memory. And the size of heap is like yeah, so heap memory is like used for dynamic memory allocation. So when we like talk about stack, it is used for static memory allocation where the size of the stack is like known before compile time. But assuming we are in a need of a program where we depend on some kind of like input from the user. So during runtime, we assume that user provides the stack size or like the memory requirement size. So in such a case where user is providing the size of the data which needs to be allocated, in that case we'll be making use of heap. Because if we like already create a stack of 5 integers, but during runtime if say user like inputs 6 as the size of the memory which is like needed, then in that case stack won't be helpful. It would lead to stack overflow issue. So dynamic memory allocation would help there. And so the problem with heap, so problem with stack is the stack overflow, but with heap we have this fragmentation issue. So heap will have like holes created, and if at all there is a requirement for having a bigger memory to be allocated, then we won't be able to like allocate this memory. I'll talk about fragmentation in the next slide. And also heap will grow always in the opposite direction as compared to stack, and we'll see why this is like needed in the coming slide. And also as we have like seen, for every thread we have like every thread has like its own stack, but all the threads will share one common heap memory. And apart from that, data like in heap on heap should be explicitly freed, because unless and until like you call this free function, the data will be there in on heap. But that's not the case in stack. So in stacks, the data will like automatically get deleted once we are like out of scope. And this heap size can be like changed based on it, because we are making use of this dynamic memory allocation for like heap. And heap memory is always slower because we'll have to like explicitly allocate and deallocate basically, but that's not the case in stacks. So when we talk about this fragmentation issue, assuming this was the heap memory, and we have like allocated dynamically this much amount of like space. So whatever like is there in this green color is the allocated memory. Now user will like say free all these memories. So he's freeing, say let's say like one integer is freed, another integer is freed. So whenever we like free an integer explicitly, there will be like holes created. Now, if at all there is a new requirement where we want to dynamically allocate 3 integers like worth of data, but if we see that there is like no space to allocate this memory here, but overall you can see that there is like 3 integer worth of space, but we cannot allocate it because continuous space is not there. So this is that fragmentation issue which I was like talking about. And the reason for why stack and heap grow in the opposite direction, so this is simply because we have to like prevent overlapping. So that's the only reason why we have stack and heap growing in opposite direction. if at all stack and heap are like growing in the same direction, then there would always be like this overlapping kind of issue. So in order to like avoid this overlapping issue, so we have this stack and heap growing in the opposite directions. So that's it I had in this video. In the next video, we'll deal with this scheduling concept. So thank you for watching.